Hello friends, welcome back to the bench. Today we're gonna take a look at the Pyle, what was it, PCAU46BA. Every Pyle device has some kind of design issue, but this one has a major one. You won't believe what's inside. Let's take a look. Alrighty, so the device is obviously fixed, but what was wrong with it? This is actually kind of curious, and this is probably the worst design issue that I've seen on Pyle devices. So this was the chip that broke, right? The chip that we replaced. It happens, right? But what would cause it to break in this fashion? It literally, almost exploded. So one possible cause is that I've seen personally was a hit of a thunder, but it didn't look like this. This is kind of a fused together. It got really hot over here. In the ones that I've seen that were hit by a lightning, it was literally exploded. The little pieces were missing from the chip. This got really hot, extremely hot. So this chip can be this chip, by the way, it says 2 times 120 watts per, so 120 watts per channel. This is actually 25 watts per channel, and it is designed to work with 8 ohm speakers. So you would have like 50 with 4 ohm speakers. Well, not quite, but you would have more power on 4 ohm speakers and even more on 2 ohm speakers. But this is designed to work with 8 ohm speakers. This is not powerful enough. This is a little chip, right? Little IC. This is not gonna push too much power through it. And the supply voltage, absolute maximum, 25 plus and minus. And guess what voltage are we supplying it with? 25.8 volts. This is our supply voltage for this chip. So we're obviously overpowering it, and that's probably what caused it to break this way. So first we have huge power, huge voltage at the very maximum and a little bit above. And usually speakers are 4 ohms, and whoever used it with previously most likely was using 4 ohm speakers. So if you crank the volume all the way up, yeah, it will result in something like this perhaps. So what we did, and as you can see, just a quick recap of the typical application over here. This supports split rail, and it is, in this case, it is supplied by a split rail. Here we see it on a single rail, so the negative VS goes to ground, and the speakers are also connected to ground, and a negative feedback over here to our non-inverting input, and yeah, that's pretty much it. What it claims to do, no pop at turn on off, and indeed I haven't noticed any pop turning it on and off. Thermal overload protection, I'm not sure about that. I'm really not sure about this thermal overload protection. This would be a question mark. So what we did, we replaced it with the same chip, same inputs, same outputs. It's just a variety, the B at the end, same application circuit, but it allows up to 35 volts for the supply voltage, plus minus. So this chip will not burn the same way as that one. Plus, that one is 25 per channel, this one is 30. And indeed, it is 30. I even got a little more than 30 from it, like 31 watts RMS, without huge distortions. Anything more than that causes huge distortions. So our maximum volume is around here. This is roughly the maximum volume, so around 80%. Anything above that causes distortion, so even with the high power speakers, it's not gonna sound good. Again, I was testing it on 4 ohm loads. This is designed for 8 ohms, so I wouldn't get, I don't think I would get, or maybe on 8 ohm speakers, it would go all the way to 100 to get 30 watts on the output. That's actually a good point. That's probably what it is. But it definitely works on 4 ohm speakers and 4 ohm load, the non-inductive load. You just have to remember not to crank it above this level roughly, right? Don't go crazy on it. As long as these are set to the middle, right? Because if you crank these up, then the volume needs to go down a little, so to compensate. That is the solution to our problem, but I found even more. Take a look at this. Here we have 3 linear regulators. These two are 12 volts, and this one is 5 volts. And the input voltage, again, 25 volts, 25.8 volts. It goes through these, all 3 go through these 3 resistors, and as you can see, there are no heat sinks on them. And yes, it does get pretty hot. As you can see, I can keep my finger on it, it's not going to burn me, but it is, I would say, I would definitely put the heatsink on it. Unfortunately, there's no room for one. I tried to do something about that, but there's basically no room. Second thing, you see that empty spot over there? 1, 2, and 3. These are places where we meant to have capacitors. And why do we need those capacitors? Well, as you can see, you don't necessarily need them. It works without them, and that's probably was the thought process of whoever decided not to put these caps there. But if you know anything about linear regulators, like these are basically a network of transistors. And what happens in the complex transistor configurations, it can start oscillating. To prevent that from happening, that's why we put capacitors both on the input and on the output. But on the input, probably, well, in my view, they should be both on input and output. These are probably output, or I didn't check, but basically there is 1 cap per each regulator, and they are missing. So before I put it back together and make it available for sale on eBay, the link will be in the description of this video, I will put those capacitors over here, because we even have the markings 220 micro at 35 volts. So this is input capacitor. If it was output, it would have a lower voltage. So these are all on the inputs of these regulators. So that's what I will do. And now this is the device that can actually work. Before, so if you buy this new and you have this chip that is largely over voltaged, then you will end up with this. This one, on the other hand, is completely upgraded, and it should work really well. So this is real power is 60 watts per channel. Sorry, 60 watts in total, 30 watts per channel, reliably, and you can push it even a little further. And you could upgrade it to by 5 volts if we increase. I didn't read the spec actually on that, but all these are at VS 23 plus minus. we're using it at 25. If we raised it to 30, which should still be comfortable for the chip, we could probably get 35, maybe 40 watts per channel, which would make this piece an 80 watt amplifier, as long as the main transformer actually allows that, because we're also limited by the power delivered by the transformer. But right now I definitely measured 30 watts on the output, and that's what I wanted to see. So this is perfectly working. Now let's just add these capacitors, put it all back together, and if you want it, it will be available. Alright, thank you very much for watching, and I shall see you guys in the next one.